So that one fits right here. All right. While we're going from solid to liquid, we're adding heat, but while it's melting, it's not changing its temperature. All right. Now we're back to where we can change the temperature again. This is liquid water then. All right. So this is ice here, and this is liquid then. We're in the liquid state at this point. Okay. It's all water, but the equation is the same. Just that this Cp for liquid water is different from the Cp for ice. So we still have Q equals mass times that specific heat times the change in temperature. It's just not the same Cp. It's a different Cp here. So we got the water in liquid state right here, and we're adding energy to it. The temperature's starting to rise. We go from 0 degrees C all the way up to 100 degrees C. The freezing and melting temperature of water is 0 degrees C. The boiling and condensation temperature of water is 100 degrees C. Okay? So, we get to that point where water's ready to boil. Alright? It's boiling away and it's turning into steam. And while you're boiling the water, the temperature won't change. You can try this at home. You can put a cooking thermometer in a pot of water on the stove and stick the thermometer in there, and for the most part, the boiling water stays at 100 degrees C. It doesn't change. Okay? The steam right above it is going to be at 100 degrees C. It might be slightly above it because it can increase a little bit. But until you heat up the steam some more, it's not going to change its temperature. Okay? So while it's boiling, everything kind of stays the same temperature. Okay? So guess what equation we're going to use there? Can't change the temperature. So which equation we're going to use there? Okay, delta T, the change in enthalpy. All right, so it's Q equals the mass of the water we're working with times that change in enthalpy. Remember, this enthalpy is different from yesterday's. This enthalpy is what's holding the molecules together. Yesterday, it was the bonds that are holding the atoms together. It's a different thing, okay? Got that? All right. So there's energy holding those atoms together. And if you put energy, well actually, what happens is you put energy into what's holding them together to get them to split apart. That's what happens. As you add more energy, you can get them to split apart. Okay? So, we can get the water molecules to separate from being liquid where they're kind of hanging together, just sticking to each other, and separating into steam where they're further apart. That's what's happening in this area over here. Okay? So we have liquid here, and then we're going to have steam up here at the top. Now steam, you can change its temperature. So if we can change its temperature, we can use an equation that has a change in temperature value. Okay? So Q equals mass times the specific heat for steam times that change in temperature. That's up here. That's where it belongs. Yep, Cp. Okay, that region up there. Alrighty then. Let's look at some values then, okay? The specific heat for water in the solid state for ice. This Cp for water in the solid state is 2.05 joules per degree C per gram. 2.05 joules, that's our measurement of energy, per degree C per gram.
Is that a time?
Yep, times. I could use the dot instead, that's fine.
What is it multiplied by? Times what?
G for grams. Now, these are not variables. These are actually units of measurement, all three of these. You don't plug numbers in for degree C or for G. That's an actual unit of measurement. Okay? All right? So just yesterday, or this morning even, we were able to cancel out moles because moles went on the bottom, right? It was per mole. All right? Well, this time it's per degree C per gram. So now this CP is this CP right here. Okay, that's the value of that CP right there. This delta H right here, this is when we're going from, if we're putting energy in to make it melt, it's a positive number. We're adding energy into the system, so that we're adding energy into those molecules to get them to sort of loosen up a little bit so they're not stuck together in place, but sort of sticking together, moving around each other, make that liquid. All right, that delta H also has a value, and that is delta H for ice is 334 joules per gram. And that's that delta H right there. Okay? Remember, every different substance is a different specific heat, and every physical state of any substance has a different specific heat. So ice has a different specific heat than liquid water. Yeah. What now? This is 334 joules per gram. 334 joules per gram. Could do it in moles, and I have the numbers for that, but you know, it's really more often done in grams than moles anyway. Okay? All right, so this specific heat's got to be different from this specific heat, because this is the specific heat for liquid water, that's the specific heat for ice, for solid. Okay? So we need a value for this specific heat. And this specific heat is 4.18 joules per degree C times grams. Okay? So this is the specific heat for liquid water. Four point one eight. 4.18. All right, just like specific heats are different between one physical state and the next for the same substance, the delta H's are going to be different for the two different transitions here. This is transitioning from solid to liquid or liquid to solid. This is transitioning from liquid to gas or gas to liquid. So this delta H is going to be different from this delta H. Okay, this change in enthalpy up here is 2.02 joules per gram. Nope, hold on, let me check that again. That's incorrect. I'm looking at the wrong number. It's 2,260 joules per gram, so let's make that different here. 2,260 joules per gram. Okay? That's the delta H for the transition between liquid and gas water. Okay. Oh. Pull out? Okay, she's not here today. Does it matter? And neither one of them are here today.
So if we get someone to be here.
Okay.
All right.
I'll try to remember.
Well,
Okay.
thank you.
All right, sure. Hopefully I'll remember that. Okay. A lot more energy here, isn't there, than down here. Okay? You have to put a lot of energy into water to get it to be steam. Huh? Down here? That's grams. It's not a number at all. It's a unit of measurement. Okay. Every physical state has a different CP, so we got another CP up here we got to come up with, all right? Specific heat for gaseous water or steam is, let's see, that's CP is equal to 2.08. Hold on a minute, I'm sorry, it's 2.02. I got different values written down here, so I got to be careful here. 2.02, not 2.08. Hmm? 2.02 joules per degree C and per gram. And that CP goes there. And this delta H is this delta H right there. So this is for solid. This is for the transition between solid and liquid. This is for liquid. This is for the transition between liquid and gas. And this is for gaseous form of steam. So we're ready to start doing some math now. We're getting close to having the skills we need to do the ice cream lab. Huh?
What is enthalpy?
Stored energy. It's not every kind of stored energy, but that's good enough for high school. Okay? Well, somebody asked me yesterday, is that potential energy? Not every kind of potential energy is stored energy, is enthalpy. Okay, but most of it probably is. If we put, when you get on a roller coaster, they crank you up to that first big old hill, that's really not enthalpy as I understand it, but that is a kind of potential energy. So not every kind of enthalpy is that kind of potential energy, but it is essentially a kind of potential energy. Okay? I mean, you guys, your body basically functions on the energy provided by simple sugars from plants. Either that or something else eats the plants, and that becomes you eat the, what is it called? It's calories from meat. You can eat calories from meat too, but essentially it all comes down to simple sugars from plants. Okay? Plants form the basis of our food pyramid. All right? Without plants, we all die. Okay? So we get the energy from those sugars because you're essentially running a combustion reaction in your body. All right? Kind of like an engine. Yep, your body is an engine. What do you think? Let's see, what was the name of that movie? Those three movies where people were the sources of energy for the machines. Matrix, the Matrix movies. Y'all remember that? Y'all didn't watch the Matrix movies? Oh man. Anyway, okay. All right, let's take a look then at how to do some calculations with all this stuff. Okay, what can we do with all this?